and good morning, good afternoon, or good night, whatever it is to all of you. It's my pleasure to be here today to present some select new features in Abacus 2022. The agenda is shown here. I'm going to spend some time talking about structural mechanics and material-related developments, and then the always popular topics of contact modeling and high-performance computing. Before we get into it, I will mention that many of you are probably familiar from years past that Abacus was on an annual release cycle, and you could expect new features every year. We reached a point where we had developments done. The projects sometimes have different scopes. Some projects take longer than others, and we found ourselves in a situation where something was ready for customers to use, but it was sitting on the shelf for 6 months or 8 months or whatever before we could get a release. So we've kind of moved towards a more frequent release schedule now. We call them hot fixes or FD releases. Every couple months, there's a new release with some new functionality available. So you don't have to take it if you want to stick to annual or whenever. It's up to you. But we do have new functionality coming out every couple months. And as I go through the presentation and talk about these new features, I'll also mention the release with which they first become available. I got a lot to talk about here today, and as always, limited time. So I may try to hurry through some of this stuff and try to get through and leave enough time for questions. So with that, let's jump right into the topics. So first thing I'd like to talk about is a very, very interesting enhancement called material properties as a function of material point information. So many of you, I'm sure, are familiar with the field variable capabilities in Abacus. That allows us to make material properties a function of some variables that can vary with space or time. That's a very powerful capability. What we've done here is extend that field variable capability to allow properties to now depend on solution variables, in particular scalar valued material point quantities that are available for output. This type of functionality was previously available only through subroutines such as USD, FLD, and explicit equivalent. Now can be done completely through the keyword interface. An example here is shown on the left. It's kind of described, at least, is the ability to make a plasticity definition have different behavior and tension and compression. You can see the kind of a keyword template here for there. I'll jump right to the next slide and just shows an example of what the keyword interface for something like this would look like. Very simple. We're making the plasticity definition dependent on the LODI, which is plus or minus 1, depending on whether the material is in tension or compression. And then you can see the resulting uniaxial response from a single element test case. So very powerful functionality, first available in FD04 21, FD04. So it's been out there and available to customers for several months now, and we've already got some feedback from some customers that have found this to be very powerful and useful in their applications. Next few slides, I'm just going to probably go through fairly quickly and describe some new material models that are available in Abacus. The first is the Villanis-Landau hyperelastic model, first available in 21 FD04. And what this model is basically about is it allows us to take a test data curve and exactly reproduce that curve in the simulation. So very similar to the Marlowe model that's been available in Abacus for many years, with the exception that this Villanis-Landau model now enables exact representation of the test data in both tension and compression. And you can see the example here where we have a material test curve that spans both tension and compression, and the simulation is able to reproduce that test curve directly. By way of comparison with the Marlowe model, you can see it can represent the test data in either tension or compression, but not both. So very convenient if you want to exactly represent your test data without going through a complicated curve fit. Another material-related enhancement is the extension of some of our pressure-dependent plasticity models to include anisotropic plasticity. In particular, Drucker-Parger and crushable foam, both existing in the software for many years, can now be combined with the Hill plasticity model, which has also been available for many years. Just these particular combinations were not allowed. So this improves flexibility of calibration particular for example, with multi-scale materials and composites and so forth. Next enhancement, which was a very popular request from customers, was the introduction of no compression and no tension elasticity into Abacus Explicit. This capability has been available in standard for many, many years, and a number of customers asking for this capability in Explicit, so that's now available. Typical use case is modeling, cables, for example, with beam elements, or perhaps something like a fabric, whatnot, and with the shell or membrane elements where we don't really have any compression stiffness, so to speak. Another material-related enhancement is the introduction of the concrete damage plasticity material behavior with beams. So concrete damage plasticity has been available in both standard and explicit for quite a few years for continuum elements. And we had a bunch of requests from, in particular, the building industry, with a common workflow being earthquake engineering, or survivability of buildings becoming more important. So modeling these beam structures, these buildings with beam structures that are physically built with concrete, is now possible in Abacus standard and explicit. And if you look, I should have mentioned this before, maybe up in the corner here, I'm listing the releases with which this is first available. And probably a good time to mention also that I'm giving you a little sneak peek ahead. Right now, we just released Abacus 2022 GA, and this first hot fix, or FD01, will be available shortly after the new year. So this is a very interesting enhancement related to materials. We call it Plasticity Corrections. And the concept here is described in the words. I'll get to the pictures, which are more interesting, I think, in a moment. But the idea is to provide an estimate of a plasticity solution, but with a purely elastic material properties. So this is obviously applicable when plastic deformation is localized. So, if plastic deformation is significantly affecting the global response of the model and introducing large deformations and so forth, then this really doesn't make much sense. But it's a very powerful capability and useful capability, for example, in durability analysis. You're doing fatigue calculations at fillets and so forth, life predictions. The benefit being we can get an entirely elastic solution, means we don't have to deal with convergence challenges, and still be able to take into account the nonlinear effects of the plasticity. Based on the so-called Nuber or Ginkgo corrections, and I'll describe those in a moment, there's no effect on the solution since this is strictly an output variable, and a couple other restrictions or limitations listed there. Isotropic only materials, and we got to have some tabular plasticity curve in order to evaluate these corrections. So here's what it looks like. Two examples here on the left and the right. We're looking at stress strain curves. This triangle here represents the purely elastic solution. So, you can see we've exceeded the yield stress, but and of course an elastic solution doesn't know that. It just keeps following the elastic curve. So what these corrections essentially do as a post-processing exercise is follow some curve to essentially match the strain energy density under the triangle here in the Nuber correction. And then under the Ginkgo's rule, it follows the area under the curve rather than a triangle. So I think that should be pretty obvious that the approximation by Ginkgo's rule is probably a little bit better than the approximation by the Nuber rule. And there's an example here looking at a component from an automotive chassis. On the left side, we have the solution looking at the Mises stress from a fully elastic plastic analysis. And then we look at the results from a linear elastic analysis. Here we're contouring the new output variables that are computed as a post-processing exercise again to predict what the Mises stress would be. And you can see that both do a fairly good job of representing the solution of the elastic plastic analysis. So great new capability if you want to save some computation time and still take into account the possible of localized plasticity. And of course, you need to use a little engineering judgment here. For example, if there's singularities in your model where the stress concentration is non-physical, then you have to use your engineering judgment to filter those out, which can be quite easily done in post-processing tools such as Abacus Viewer. Next enhancement I wanted to spend a few moments describing is the strain rate filtering capability in Abacus Explicit. So I'm sure many of you are familiar that in the explicit algorithm can be a bit noisy, especially if we don't have much dissipation in the model. So here I'm talking about maybe elastic only material properties, which is not uncommon for drop testing or whatnot. But if we have strain rate dependent material properties, the noise in the solution can sometimes result in errors in the evaluation of the rate dependent material properties, and this is particularly pronounced at very small time rates. Up until the current release, we had a factor to control the filtering, essentially some sort of a filter built in that allows a more accurate evaluation of the strain rate dependent material properties. We found a few cases where this is not quite accurate enough, so we've introduced a new filtering capability. We call it time-based filter. You can see the differences here. So on the left side, we're looking at a simple one element test with a very, very small dt. So that's where the initial S rate factor sometimes came up short, and you can see it's unable to resolve the rate dependency of the material here. Three different orders of magnitude of the rate dependence, whereas the new time-based filtering is able to quite accurately resolve that time strain rate dependence of the material properties. Another enhancement, again, lots of material-related enhancements. This is related to extrapolation of yield stress. So I'm sure many of you are familiar that the default behavior in Abacus for many years is when you run off the end of your plasticity curve, which in many cases is simply a point. We hold the stress constant, and what that did in many cases is create localized plasticity regions that would grow and then sometimes result in convergence difficulties. And if you see the warnings in the message file, that's oftentimes what it means. And we have to cut back, and eventually doesn't converge, and you spend a lot of time diagnosing these problems only to find out, who knows how long later, that it was just some localized plasticity that kept you from getting results. What we're doing now is we've introduced this capability to extrapolate in a linear fashion the yield stress. So there's an example, typical material definition, where we have the elastic behavior, and then we have a single line representing the plastic behavior. Here is the previously existing behavior in Abacus. When we reach the last point on this curve, constant, meaning it could very easily deform. The new behavior is we're going to linearly extrapolate that curve. And what that does is allows us to potentially in many cases keep running and avoid those convergence difficulties. Of course, in both cases, the results may or may not be physical. So it's again really up to the user to use their engineering judgment when looking at the results. Obviously, if I've gone up into this range and it's beyond the ultimate stress, then my results are no longer physical. But for those cases where it's localized and you're not interested in that localized behavior, maybe the global response is more important. This is a good capability to keep the thing running on the machine and avoid some convergence difficulties. The default remains constant. So if you want to enable this capability, you need to check a box to turn it on. Another enhancement related to mechanics is results mapping for shell elements. If you've attended previous release webinars, last year, for example, we spent a fair amount of time talking about the external field capability, which was a unification of all the different mapping technologies that have been available in Abaqus for many years. This is an extension of that now. The external field capability now able to map shell through thickness results on shells for homogeneous shells and also for composite shell elements. So, and then you can expect further enhancements to the external field and the mapping capabilities. This is really an area of active development for us, and we'll be further extending the external field and mapping capabilities coming up in future releases. And if you have requirements, would be very thrilled to hear from you to help guide us in our developments in this area. I think this is the last enhancement I have to talk about before we switch gears to contact. Particle methods have been available in Abaqus for, I think SPH was first released almost 10 years ago. A few years ago, we extended that to include the discrete element method. And we also have a slightly more particular capability called LKM, which is intended for modeling, in particular gas dynamics and airbags. So SPH and DEM are really the main particle capabilities that have been available in Abaqus for quite a few years now. And what we've done is took a step back and revisited the architecture behind these technologies, unified some of the algorithms, particularly when it comes to tracking particles and so forth, and just improving robustness, particularly with regards to parallel processing. The goal there really is ultimately improve performance. And here's an example here where we're seeing some of the benefits of that. This is essentially a fluid structure interaction. We have the structure of the blades here modeled with shell elements and so forth, and then the fluid, if you will, is being modeled with SPH particles. So about a 20% performance improvement now with the improved architecture. And again, look up in the corner. This is will become first available in 22 FD01, so shortly after the new year. Okay, so that's what I had picked out for today in terms of general mechanics and material enhancements. Now I'll spend some time talking about various contact modeling enhancements. First is the evolving feature edge capability that we developed in Abacus Explicit over the last few releases. I've talked about that for a while. Just a quick overview for those that may be not familiar with it. The idea is there's many scenarios where feature edges are important to accurately resolving contact. The default had been to evaluate feature edges in the initial configuration of the model. What can happen sometimes, though, as models deform, feature edges evolve and come into existence, and those feature edges would not be taken into account. And that would result in non-physical penetrations, for example, what you're seeing here in this picture in the middle. So our solution to that was to introduce a capability where the feature edges evolve as the analysis proceeds. Of course, those good things don't come for nothing, and there is a performance penalty associated with that. So as we set out to develop this capability, we set a goal that no more than 10% of performance penalty, additional computational time, we activate this feature by default. So we've had evolving feature edges in the software for a couple of releases now. In 2022, we've reached our 10% threshold, and we now turn these on by default. So the benefit of this is you don't have to think about it. It's just on by default, and you don't have to run a simulation and discover after the fact that your results are no good. So that's really where the 10% comes from. 10% we think is a small amount to pay as opposed to running a simulation over again, or perhaps worse, making decisions based on incorrect results. You can, of course, turn this off if you prefer to revert to the previously existing behavior. Next enhancement is related to general contact in Abaqus Standard. In prior versions, we essentially made a large static allocation of internal contact elements and nodes to account for potential contacts. In many applications, most of those remain inactive because they're only needed if there is active contact. So that can lead to performance drag and an increased, due to tracking and so forth, and an increased use of memory. And we sometimes, not very often, but occasionally saw error messages where the static allocation was not sufficient. This would be in cases where essentially every element and node in the model was somehow in contact with something else. So we've been a fairly significant project to move from static allocation to dynamic allocation. So what I mean by that is we allocate contact elements and nodes based on what is initially in contact, and then as new facets and nodes come into contact, we can expand the allocation and introduce those new contact elements and nodes on the fly. So what we see is in most cases, on average, a 10 to 20% performance improvement is common. And the chart here that I'm showing on the lower right-hand side of the screen is just a cross-section of various contact models. You can see it, there's quite a spread here, which is really reflective of the amount of contact that exists in the model. Right? The biggest improvements are going to be coming from models that have large numbers of contact faces and nodes with relatively few of those that come into contact. Benefits a bit less when you have large numbers of percentage-wise of the contact elements and nodes coming into contact throughout the simulation. So this is in there and on there by default. So out of the box, if you have general contact models, you can expect to see some performance benefits due to dynamic allocation. Another enhancement in Abacus Standard is the introduction of step-dependent contact interactions for general contact. So up until now, contact was defined as part of the model and existed for the duration of the simulation. If you recall back under the contact pair algorithm, many years ago, we had the model change capability that allowed us to remove and then reintroduce contact pairs as the simulation proceeded. So this is conceptually similar to model change, although it uses a different interface. We can now introduce and remove contact interactions as the simulation proceeds. So this is a very common requirement when we're doing maybe assembly analysis or simulating some sort of manufacturing process and so forth. So that's available now in 2022 GA if it's needed for your applications. And another enhancement, this here, we're switching back into Abacus Explicit. A very popular request from customers is to take into account beam cross sections when we have beam elements in contact. So recall in general contact in Abacus Explicit, when we have a beam element independent of what the cross section actually is, general contact up until now has treated those beams as cylinders, which is okay in many applications, but does introduce some limitations in other applications where that cross section shape significantly impacts the response to the model. So here's an example here of the beam contact capability. Here is the wire plot of the representation. In the middle, you can see we have a hex-shaped profile and then a rectangular shaped profile, and we're sliding those together. And a zoom in to see what looks to be a quite physical capturing of the response, taking into account the actual shape of the cross section. So that's available starting in 2022 FD01, so right after the start of the new year. So that's it for contact, at least what I'm going to talk about today. There's much more that we just don't have time to cover. So the last segment of the presentation here today is high performance computing. So this is really really what we hear day in, day out, really from customers, is the importance of high performance computing and getting results fast. So actually, many of the enhancements I talked about already are related to performance, the general contact, dynamic allocation, feature edge, all ultimately come down to performance enhancements. What I'm going to be talking about here is more solver related and leveraging high performance computing hardware and being as optimum as we can in how we leverage that hardware. And in order to motivate the discussion, I'd like to just spend a quick few minutes introducing some terminology so that we make sure we're all speaking the same language. So here is a schematic of an HPC cluster. We have compute nodes in blue. You can have many of those connected together, potentially with switches and interconnects. Within each compute node, there is what's called a socket, or oftentimes called a processor. So this is colored in the red box. Typically today, most compute nodes have 2 sockets, but that can change over time. And then within each socket, we have some number of cores. So here we have compute nodes that have 2 sockets with 8 cores per socket. And we can potentially plug GPUs in to these compute nodes as well. So this is really a hardware view. If we look at how the software leverages that hardware, there's a couple modes of execution. First is the so-called shared memory parallel. What this means is a single executable process on a compute node with multiple threads of execution. So if I looked at top or performance monitor or something, I would see one instance of abacus.exe running on this compute node, and it would be running parallel using threads with information shared as necessary using the shared memory of the system. So that's one mode, SMP. Another mode is so-called distributed memory parallel. Here, what we do is we have multiple executable processes running within their own memory space, and then data is communicated between processes via a message passing interface. So this example here, same compute node, I have 16 instances of abacus.exe running, each with 1 thread per process. And then the communication is through MPI, messages passed between the processes, not through shared memory. So this is one potential DMP configuration, and there's other configurations. For example, I can stack multiple compute nodes together. And again, so this is pure DMP, 16 processes per node, and then 2 nodes. So here I'm running 32-way parallel. It turns out that neither one of these is necessarily optimal, and that is what leads us to another mode of potential computation, which is called HMP, or hybrid message parallel, which combines SMP and DMP. So here's an example here of HMP where I have 1 process, executable process per node, 16 threads per process, and so on each compute node, the communication is by shared memory, and then across compute nodes, we're using MPI. So it's a combination of SMP on a single compute node and then DMP to scale across compute nodes. And there's many more possibilities. So here's a few here. That are possible. Here we have 2 processes per node, 8 threads per node. Here we have 4 processes per node, 4 threads per node. So all 3 cases are 32-way parallel. So ultimately we're using 32 cores, but it turns out the performance characteristics can be quite different. I'll talk a little bit more about that in a few minutes. And just for now, I'm just going to mention that the parameter threads per MPI process is the parameter that you use to determine the number of MPI processors per compute node, which implicitly defines the number of threads per MPI process. So here, the next few slides, I'm going to talk about Abacus Explicit. And Explicit has been based on DMP for really since the domain parallel was first introduced over 15 years ago now. Just recently, we've been developing a hybrid version of the Explicit solver. So we are able to run in shared memory threads and then mixed with DMP MPI. And that's really a major area of development. I'm not showing the results on this particular slide, but I will show some results of HMP Explicit in a couple slides. What I'm showing on this slide is really the work that we've been doing to extend the scalability of Explicit up to very large numbers of cores. This particular example is running in pure DMP mode, not HMP. And you can see some model specifics here. So 21 million elements, 90 million degrees of freedom, so a quite large model, 600,000 increments, so quite long running in terms of increments. So we're going to run this in double precision. The hardware here is the AMD EPYC platform with 64 cores per processor. And these compute nodes have 2 sockets, so we have 128 cores per node. And this example is element dominated, so it doesn't have general contact. No need to worry about contact in this. And this really represents a best case scenario, assuming that the load balance based on the domain decomposition is fairly even for each domain. And what we're seeing in this case is scalability that is almost equal to ideal. So we're looking at 2 curves here as we go from 128 cores or 1 node up to 16 nodes, so 2,000 cores. You can see the theoretical speed up from versus the actually achieved speed up is virtually indistinguishable. We can see the actual times here in this chart. Going from 1 node, 128 cores, to 16 nodes and 2,048 cores. First of all, the wall clock time went from 62 hours to 3 hours. So went from waiting days to get a single set of results to getting several sets of results in a single day. That's probably the key takeaway here. And then also you can see that the scalability is almost matching ideal. So ideally, we'd expect about 14,000 seconds, and in practice, we got about 14,100 seconds. So pretty close to ideal scalability. Next example here is, or I just want to talk about a model. This is one of our benchmark models. We have many benchmark models that we develop in-house and use for testing of the code. We also have many customer models that we use to do performance testing. We can't show the customer models typically. That's why we build some of these realistic models in-house. One of our more recent ones is a very detailed model of a mobile device, and we're using that here in this case to conduct drop test simulations using Explicit. So this is a few description of the model here. Next slide is showing the performance and scalability results of this model. So 2 million elements, 7 million degrees of freedom, fairly small time increment here. In this case, 1 times 10 to the negative 9th. What's different about this model than the previous one is that there's general contact. So we have to take into account contact with the load balancing and the domain decomposition. And there's also nonlinear behavior, including material damage and failure. Again, we're running on the same EPYC platform, 64 cores per processor. In this particular example, we're starting at 1 node, 128 cores, and going up to 8 nodes and 1,024 cores. And again, we're very pleased with these results. You can see the speed up relative to ideal. It's not exactly on top of the ideal anymore. We do lose a little bit of the load balance as contact evolves and as the simulation proceeds and areas start becoming plastic or failing. But I think very impressive results nevertheless. And again, you can see that the wall clock time reductions are quite significant. An hour per run down to 15 minutes per run. So in the same amount of time, that means you can evaluate 4 design alternatives as opposed to 1, for example. Last slide I wanted to show you with Explicit was to some data related to HMP versus DMP. So this is the same phone drop test model that I just showed. In this case, we're running on Intel Broadwell platform, and The benefits of HMP really, or the reason for HMP, I should say, is that what we found is that we scale up in the number of cores. With DMP, remember each process equals one core, we have lots of communication overhead. So in this case, we have 448 cores. That means 448 processes communicating via MPI, which means bottlenecks increase. So that's really the goal of HMP for Explicit, is to minimize that communication overhead, use the shared memory within a single compute node to improve performance. And that's exactly what we're seeing here. As you can see, as we scale this model up on the number of cores, so these are 28 core Broadwell nodes. So we'll go from 1, 2, 3, 4, 5 nodes up to 448 cores. You can see the wall clock time of HMP versus DMP in the middle two columns, and then the performance improvements with HMP. So up at 448 cores, we're getting almost a 30% improvement over DMP using the HMP. And we expect this number to increase over time. There's still some features in the software that aren't fully supported or optimized for HMP execution. So we'll expect to see that improve over time. A recommendation that we make in terms of setting threads per process is basically we want to have number of cores per socket. So if we think back to the schematic I had earlier, 2 sockets with 8 cores per socket, we want to have 8 threads per MPI process for that particular hardware configuration. The one shown here in this example, we have 14 core sockets, 28 core nodes, so we would set threads per MPI process to 14 in this for this Broadwell platform. So that's what I wanted to talk about in terms of Explicit. I think the last topic I have for today is actually I have 2 more topics left. One of them is going to be the Iterative Solver. I'm not going to go into detail about the motivations behind the Iterative Solver. We've talked about that in the past, but just very briefly, the idea of Iterative Solvers is to enable very, very, very large models that simply can't fit in memory with the direct sparse solver. Recall the direct sparse solver, the memory requirement scales as an exponential function of the problem size. So there's just some inherent limitations to that solution technique. It's robust, it's fast, it works for sparse problems very well. But if we have very large models with large memory requirements, blocky models, Iterative Solver is really an enabling technology for those types of problems. We introduced a new Iterative Solver based on the AMG algorithm back in 2017. So fully hybrid, so hybrid execution as I've described earlier. And over the next couple of releases, we improved the performance of these solvers, particularly with things like preconditioning and various other proprietary algorithms in many cases to improve the convergence behavior of the iterative solution technique. Here, when I say convergence, I'm not talking about nonlinear convergence. I'm talking about convergence of an iterative, the iterative solver itself. In 2019, we introduced the so-called MCP version of the iterative solver, so mixed constraint preconditioner, which is a capability that allows us to expand the scope of modeling features that can be solved with iterative solvers, in particular those features that have Lagrange multipliers. That's what LM stands for. So things like hybrid elements for incompressible rubbers, or distributing couplings, or hard contact, and a bunch of other types of modeling constructs that are very popular in Abacus. Not work well with the AMG technique, but are compatible with the MCP solver. We continued improving that in 2021X to support things like distributing couplings and so forth, and very large distributing couplings, which are very common. And now in 22X, further expansion of both the AMG and MCP iterative solvers to support unsymmetric systems of equations. So things like large friction coefficients, certain material models have unsymmetric stiff matrix, and so forth. So expanding the scope of the iterative solver. I have some data points here just to show you where we stand. This is, again, an internally developed model, a powertrain model. You see some I guess we don't have the size listed here any place, but it's millions of degrees of freedom, tens of millions of degrees of freedom for this model. You can see the hardware platform here, which is Cascade Lake Intel, 20 cores per socket in this particular case, 384 gigabytes per compute node. So looking at different scenarios of running this model. First is with the direct solver. And this is a case where the direct solver is able to converge and fit in memory. We have 2 nodes, 2 sockets, 20 cores, so a total of 80 cores. So we can fit this into memory. You can see the 583 gigabytes total memory. So we're scaling out over multiple nodes in order to fit this thing in memory. The middle is the iterative solver at R22GA, so what's available right now, but in this case using the symmetric preconditioner. And then the last case, 22X FD01, so coming in a couple months after the new year with the unsymmetric preconditioner. In terms of the solution, you can see pretty much the same number of increments here, 6, number of solver passes. So this is essentially the nonlinear Newton iterations. You can translate that into here is the number of iterations within the iterative solver. Obviously not applicable for the direct solver, but with the unsymmetric preconditioner, you can see a significant reduction in the number of iterations required for the iterative solver, which directly translates into improved performance. Here we're looking at standard wall clock time. If we actually looked at just the solver performance, you'd see about a 4x increase in the performance of just the solver. Here we're looking at total standard wall clock time, which includes element calculations and so forth. So not quite the 4x that we're seeing in the solver. And then lastly, the performance factor here. So how much faster is the iterative solver with the unsymmetric preconditioner as compared to the direct sparse solver? So quite significant, 7x speed up in the total wall clock time, essentially in half as much memory. And the last point I wanted to make here is our recommendations for the iterative solver is threads per process equals 4. We found that to be the best for the most part, and this could mean potentially leaving some cores unused on a single compute node. For example, if the number of cores is not divisible evenly by 4. So last thing I'd like to talk about is cloud computing with Simulation Manager. We talked a little bit about this last year. Simulation Manager is a browser-based application for running and managing Abacus data on the Abacus jobs and managing the data on the cloud. We support multiple compute configurations. Currently 4 cores up to 144 cores. Multiple Abacus versions are supported in the current version of Simulation Manager. We support 2019, 2020, 21, and our current release 2022. We recognize that customers have continuity requirements that oftentimes require running previous releases of Abacus, and that's okay. We'd like to see you run the new versions and take advantage of all the performance benefits in particular, but we know that's not always possible. The package here comes with Physics Results Explorer, which is our 3D experience-based high-performance visualization application. And we can work with the token-based or credit-based compute licensing. So the real target for this, or at least the sweet spot today, I'd say, is burst computing or overflow computing. For example, if you have a very large job that you need to run that maybe needs 144 cores, you don't have enough tokens or hardware to run that on site. On premises with your Abacus install, you can jump right onto the cloud and run those jobs on the cloud with a large number of cores. Another example may be a design study. You need to run 20 jobs overnight. Again, you don't have the hardware or software available. You can jump onto the cloud and do that very easily, especially with the credit-based licensing, which doesn't require a commitment over a term. You're essentially paying per job. So whatever it is, $10, $100 per job, whatever it is, you can pay for the jobs as you go. So that what I'd like to do is just try to do a quick demo just to show how easy it is to run Simulation Manager. So here it is. I'm showing Simulation Manager in a web browser. So this is Google Chrome. And this is the user interface for Simulation Manager. If you have the platform, you can also click on the compass here and scroll down here, and you can see all the different applications I have available to me. I have the all-in-one license, so this has all applications, but you know, at a particular site, you know, you would see the applications that you are licensed. Simulation Manager here has a panel on the left showing the various simulations that I've uploaded and run on the cloud, and then the business area over here. For example, if I click on this analysis case, I can look and see the various files and so forth that were created with this job. I think this is probably very familiar to many of you. So what I'd like to do right now is run a simulation. So first, I'm going to create the simulation, and this is I'm going to run my my trusty flange model. I can type, and I'm going to do it's a ceiling analysis. And then I'm going to accept the default name for the analysis case. I'll talk a little bit about what that means in a moment. So I click OK, and it's going to go and create some space on the cloud for me where I can have this simulation run and so forth, and my default analysis case. So what I need to do now is upload an input file. So I'm going to do that. I'm going to select my input file, drag and drop, upload it. This is a fairly small problem. Maybe you saw it. There was a status bar there indicating that it was uploaded and saved. So pretty much ready to run. At this point, I'm going to switch to the Setup tab. Some choices here: analysis, data check, syntax check. I'm sure very familiar. As I mentioned earlier, we have a number of Abaqus versions available. I'm going to stick with 22X, the current GA, and some other options that are available to configure the solution. And lastly here, the results format. So ODP, I'm sure many of you are familiar with, I hope. For visualization in Abaqus Viewer, we have a new format we call SIM that's used by Physics Results Explorer. I'll talk about Physics Results Explorer in a few moments. And then lastly, an XML-based lightweight visualization content. So I'm gonna stick with all three selections for this simulation. So it's configured, and I am now ready to run the simulation. So I just click on Run, and it's gonna give me a few options here. So again, I mentioned tokens or credits earlier. I can run with tokens or credits. I can choose the configuration by default. When you submit the job, we're gonna count up the degrees of freedom and so forth, and pick a configuration that makes sense. But you can override that if you want. I'm going to override it in this particular case and say let's run on the 4-core configuration, which is the smallest. And then great, and away we go. We're going to run the simulation. You can see that you get some feedback here. It says it's submitting the simulation. So right now we're going on to the cloud and firing up a 4-core instance. We're gonna run the simulation. I'm going to switch over here to this tab called Logs. I think we're going to find this fairly familiar. So we're waiting for it to fire up the job. It did right now. So here we're looking at the message file. You can see very familiar information there, the data file, information there from batch pre, or the log file, etc. So we're still running standard. We can monitor the simulation if you want, showing various variables and whatnot. And I think fairly quickly this job completed. So we can look at the message file, and I think we're going to see that we're completed. It's probably still doing some work after the job, running the generating some results and so forth. But we're pretty much done running the job at this point in time. And what we can do then finally is go back to the content tab, and you can see what I have available here for content. The input file that I had was still there. The ODB has been generated. If I want to, I can download that and post-process with Abaqus Viewer. you can see that I have the sim file there and so forth. I want to look at the sim results, which I'll show you right now. We can do that. I'm just going to click this button here and say, okay, open with Physics Results Explorer. So I've had it running for a while now, so hopefully my license, nope, it did, good. My license didn't time out on me, so that's a good sign. So what's happening right now is that on the cloud, we have the server, the visualization server. So the data is being opened in the visualization server on the cloud, which can run in parallel on multiple cores. So the benefit there is you don't have to download results, potentially large result sets and so forth, and you can take advantage of high performance parallel processing on the cloud. So right now it's accessing the results data. So basically the servant is being launched on a compute instance on the cloud. It's going to open up the sim results, perform some calculations to and then ship those results off to Physics Results Explorer. So here I have the model shown in Physics Results Explorer. So this is an application running on my screen, and I can create various plots. For example, maybe I'll do a von Mises stress contour plot, whatnot, and so forth on my screen. And so this is just the quickest tour of Physics Results Explorer that I can possibly give you. And so that's really all I wanted to show, and as part of this demo right here. So you can see that was literally done in real time, live. So if there's something of interest to you there for Simulation Manager, cloud computing, and burst computing, it's really that easy. Contact your local account representative, and I'm sure they can set you up with a login and some licenses to get going on the cloud. So in summary, the development of Abacus structural simulation technology is continuing at a very, very rapid pace. I literally presented a small subset of the developments we covered in this presentation. So as always, refer to the release notes for a complete listing of everything that is new. In particular, linear dynamics, huge developments going on there, not covered in this presentation. Fracture mechanics, also huge developments going on there, and also significant developments going on with adjoint sensitivities and optimization and dynamic optimization. Just didn't have enough time to cover it all today. So with that, I conclude this presentation, and it looks like I was able to leave a few minutes for questions. So we'll switch right over to questions. I think Vanessa is going to read them. I understand they've been entered on the community, so myself or maybe some colleagues will have a chance to go back and answer those questions for you if we can't answer them today. So with that, Vanessa, do we have questions?
Yeah, thank you, Eric. Yeah, we received already some. Is pore water pressuring modeling available in Eulerian Elements in the new version?
So if I think they're looking for pore pressure, and the answer is no. That is something that's come up a number of times, something we're interested in pursuing, but it hasn't happened yet.
Okay. Any linear dynamic enhancements?
So I kind of partially answered that question with my summary. Yes, there's a lot of them. And related to AMS eigensolver, acceleration there, damping, substructures, a whole bunch. We could probably have a whole presentation just on those, so I have to refer you to the release notes for a comprehensive listing of everything that's new with linear dynamics.
Is input file for the phone drop tests available?
So we that's a good question. I'm not sure if it is. We do. I know we used to post those that were available for download. I'm not sure if that, so I'll have to dig into that and find out if that is available. We used to post the benchmarks and make them available for customers, particularly for benchmarking and so forth. I'll have to check.
Can you confirm if the CPU command in Abacus job now checks the CPU cores rather than the logical pressure in Abacus 2022?
Yes. So I believe we addressed this in the documentation and the release notes as well. So, and just for those maybe that aren't familiar with the question here, on Intel processors, we have this thing called hyper-threading. That essentially allows software to see a single core as two cores. You don't use that with Abacus. It doesn't really make any sense. So you definitely want to have that disabled, and cores or CPUs on the command line means a physical core, not a logical or hyperthread.
How is the scalability of HPC for Abacus standard?
So I presented some of the data there, in particular for the new Iterative Solver, where you could see problems, 50 million to 100 million degrees of freedom, going up to 1,000 compute cores. I didn't present any data on the DirectSparse solver, but again, we're seeing very good scalability. 500 and even up to 1,000 cores. Of course, scalability depends to a large degree on the size of the problem. You can't take a 1,000 element model and expect to scale it on 1,000 cores, but as the problem size scales up and the amount of that the software that can run in parallel, particularly the solvers, it becomes a larger proportion of the overall cost, and scalability is quite good. And just a quick mention, we've been doing a lot of work on the Iterative Solver, direct solver, I should say. Not quite ready to talk about that yet, but within the next couple months, you'll probably hear us talking about some extending the direct solver to a next level.
Could you please elaborate a bit on adjoint sensitivity enhancement? Is it compute speed or additional scripting interfaces?
So what we're doing, and I can't get too deep into this right now, but we are computing sensitivities within the Abacus solver. So these sensitivities can then be used as output variables for basically topology and shape optimization is really the key use case. So, for example, in Tosca, we used to compute these sensitivities externally based on results. We can do it more performance and more accurate by computing sensitivities within the solver. So that's really what that's all about. I'd invite you to check the documentation and the release notes for a more detailed discussion of what exactly we're doing there. But that's a very active area of development and complements the various optimization technologies that we offer as well.
Has there been any improvements in the measures in Abacus CAE? I don't see anything in the release notes.
So yes, there is. Focus of this presentation was on the solvers, but if you do get the release notes, there's should be dozens. My last count was dozens of different enhancements to CAE. Almost all of which are driven by customer RFEs. So every release, we're looking at the customer RFEs and implementing as many of those as we possibly can. So they are in the release notes. If you have the 2022 release, you'll find a bunch of CAE enhancements there.
Okay, thank you, Eric, again. I can't see any additional questions for now. If you have some additional questions, please feel free to comment on the post in the community and we will follow up afterwards. And with that, we can close today's Tech Talk. Thank you again for attending and for your presentation. Have a nice rest of your day and goodbye.
Thank you, everybody. Bye.